Welcome to a lesson with Dr. Powell. In this video, we will look at the Mobius mu function. In particular, how it talks about the top row of a Mobius matrix. Okay, so first for a poset we can look at. This poset right here represents the divisors or the factors of 60. Notice that at the top top, I've circled some of the vertices. This top structure looks like a power set. In fact, in the last video on the playlist where this is being put, actually has the posets actually have the same structure. So I did say we'd look at posets that have different structure, and I was right about this because I'm looking at this divisor poset of 60. However, I'm going to concentrate on a portion of this which has the same structure. Okay, so we're getting a lot of these here. Yet there comes the question, why is this why can we focus just on this top piece right here for a top row of the Mobius matrix and not kind of ignore the other parts? And that's what I like to talk about here. In particular, let's look at an example right here of looking at a standard basis vector and as sums and looking at the corresponding nodes, and in particular the contribution of these nodes to the top right here. Notice the contribution is 0. The contribution 0. So why is that? Why is the contribution equal to 0? Well, you can work it out and just kind of work through the process and notice that you don't even need this top. This happens whenever for factorization posets, divisor posets, or lattices. If you're out of a top poset structure, if you're not in there's always a structure at the top that looks like a power set diagram or Hasse diagram. And if you're out of that, then, and so this is like, and not only that, it's the biggest power set structure at the top, all right? So if you're out of the biggest power set structure from the top down and you're kind of, dangling down, loose down here, the contributions will be 0 to the top every time. You can test it out and see as you go. In this top power set structure, the contributions are alternate as we saw, but then out of this, actually, because you actually do get power set structures coming from here that are completely contained, that don't ever get to the top here if you kind of think through that. And so that's basically an intuitive reason why. I mean, take a look at this one right here. You have power set structure right here based off of this. It doesn't ever really quite get to the top. We can talk about that a little bit. So in particular, wow, I relabeled everything. In fact, it looks kind of like I flipped everything upside down. But something that's true about divisor posets is that you take the dual poset or the opposite poset, and it's isomorphic to the original. That things turned upside down, it looks the same. But not only that, this looks a little bit different. Instead of numbers, I have sets. What is that? Think of these as being a prime factorization. 2 times 2 times 3 times 5 is 60. 60 is on the bottom. 2 times 3 times 5, that's 30. Oh, those are numbers like 60, 30, like in that, everything's turned upside down. Notice, okay. So, and then there are no prime factors with number 1. So that could be, so at the top, we could have, the number 1, bottom we could have the number 60, 30, and so forth as we go here, the number 5. Now, to get back to the actual numbers that we had, we could just these different numbers that I'm putting right here, what if we just put a 60 on the top of it? 60 divided by 60, that's 1. That's 2. Hey, that's on that level. 60 divided by, so right here we do 60 divided by 5 is 12. Okay, so that's at, and then we got 6 divided by 1 is 60. Sorry. Okay, so we can kind of look at that and check it out, and we notice yes, we have a 12 there, 60 there too. Okay, so this is looking promising. So really, that's one way we can think this structure looks the same. But why is this nice? Because actually, we can actually see a power set happening here. Of course, turned upside down, but posets turned upside down are isomorphic. The poset isomorphic, they look the same, just upside down. Here we have empty set, 5, okay, well, looks great. So we have a power set, we can see that structure. So in thinking about what's outside of it, notice what's outside of this top portion. 2, 2, 2, 2, 5. Those don't look like sets. Those look like multi-sets where there's repeats in the entries. So essentially, in fact, every one of these is a multi-set. So what we're really doing is we're trying to throw out the multi-sets. Throw out the multi-sets here in this particular depiction, and then just take the -1, 1 contributions. Like from level 0, like right here, you have a -1 contribution. From this level, so you have from this level, you have a -1 contribution. From this level, you have a +1 contribution. From this one, a -1. From the top, a +1 contribution. Going right up. And out of the structure, you're going to have 0 contributions. Okay, so how can we pick that out? How can we pick out when we have a multi-set versus just in this level going up? And that's what we're trying to talk about in this video, is the Mobius mu function. All right, and notice here we're saying 60 over, and so forth, because we're going to be flipping things upside down and looking at a set. We're using the mu, Greek mu letter. Mu of n, where is, what is it going to be? It's going to be 0 if n has a square factor. If it has a repeat in its prime factorization, it's 0. -1 to the k, if it doesn't have a square factor, where k is the number of distinct prime factors, or prime divisors, prime factors of n. All right. That's like the size of the set, right? 2 things. -1 to the squared, that's +1. Okay, 3 things here, -1 cubed. That's a -1 contribution. 1 thing, okay, -1 to the 1, where k represents how many things are in those sets. And that can kind of come about here. So that's a Mobius mu function, which is often used in counting different things. But what it gives us is it gives us the top or elements of the top row of a Mobius matrix. It gives us those top contributions from the standard basis vectors, as we've been discussing, between positive and -1. And not only that, it actually throws things out for us. You notice, see this 0 here? It throws out repetitions. So this function is, so we're looking at the top row of a Mobius matrix on the structure, not of the power set, but the whole entire thing. But the Mobius mu function tells us that these entries will be 0 in the computation. It's just another description of it, really, of how to get that, but via this idea. So you can define the Mobius mu function in such a way. Okay, so, and in particular, in this particular example, we have the Mobius mu function 0. So if we're just thinking about the factors themselves as being the sums, we can figure out the nodes in that case. And if we do, we figure out what's new at the top. And what's new at the top is actually the Euler phi function of 60. What is the Euler-Phi function of 60? It counts how many things are numbers 1 through 60 that don't share any common factors with 60. I had one of my previous videos actually talked about that. The Euler-Phi function is an example of counting something that's new. And that's exactly what this is computing. If you like, you can kind of think, okay, there's 60 multiples of 1. Maybe go up here. 60 multiples of 1. There are 12 multiples of 5, 20 multiples of 3, 30 multiples of 2, and you can keep on going down the list down here. Now, what's new at the top out of the 60 multiples of 1 that have not been counted by anything previous, which are the factors of 60? Those are things that don't share common factors with 60. That's going to be the top node. So the Mobius mu function can actually help us to compute the Euler-Phi function. Of course, it's not the simplest. I mean, it's not. There are much easier ways of computing the Euler-Phi function, but nonetheless, it does make an interesting connection, which does have applications in its own right. Okay, and especially if you're kind of formulaically trying to just talk about how something can be moved from sums to nodes and vice versa. Okay, so make that computation. We get the Euler-Phi function of 60. Here's yet another example on this exact same poset. All right, or perhaps it's a different one actually. I think it's a different one. Okay, but it's on a divisor poset still. All right, we're going to be looking at primitive bit strings, counting them. What's a bit string? Well, these are going to be binary bit strings with ones and zeros. And here's examples of ones that are not primitive. They are made up of repeating blocks of things. But not all strings of ones and zeros can be decomposed into repeating blocks. Anything that can't be decomposed into a repeating block is called primitive. Kind of think about it, something that's new, not counted by a repetition of something previous or before. So perfect candidate for something you can count on a poset as something that's new, as a top node, question mark. All right, so in this particular instance, let's consider the number of primitive bit strings of size 36. Well, how many bit strings are there of size 36, that binary bit strings? Well, 2 to the 36. What about ones that are made up of repeating blocks of size 12? Notice 12 is a factor of 36. 18 is a factor of 36, and so forth. We get all the different factors of 36 for the different repeating blocks. So how many things come from repeating blocks of size 12? Well, 2 to the 12th determines one block. Well, that one block determines the whole thing. So therefore, there are 2 to the 12th of these guys that have a repetition of size 12, and 2 to the 18th that have the size 18, and so forth. We can go down and get all of these. Now, notice that we want to consider the top power, the biggest power set structure we have at the top. And this is actually it, because if you went to 3, I don't see any power sets based off of 3 elements here. This is the top guy, so everything else will be thrown out. The Mobius mu function actually will take care of that. In fact, notice that I just simply threw out everything that it wasn't in the top structure, where the Mobius mu function I knew was going to yield 0. And I just focused at the top. Notice 2 to the 6, actually that position will contribute a +1 to the top. This level contributes a -1. The top contributes a +1. You can always kind of think the top is going to contribute a +1 to itself. So right below it's a -1, and the one below that's a +1. So you can kind of keep it straight that way. 1 at the top, -1 below, and then 1 at the way bottom. So in fact, you don't even have to compute these Mobius functions, but we actually know, I mean, if you just know that structure, you could just write down that top row of the Mobius matrix, at least the portion that we need, right, just for that top poset structure. and put in those. It's just inclusion, exclusion, if you like. But this does compute right here the number of primitive bit strings of size 36. Thanks for watching.